right, so well, I'm going to continue where we left off yesterday. I have some animations, so I'm going to go back and forth. I think only once here to show you some pictures since it's the last day and it's in the afternoon, so animations are good. Yesterday, we finished in this part where we were talking about a particular case of distributionally robust optimization when the cost function is not a metric. By the way, I really like the discussion that was that unfolded like just a few minutes at the end of Pepe's lecture. I think so. I think I'm going to mention some comments about that because I think that was a great question. I mean, some colleagues. I mean, I've had this discussion with people who do like a colleague that I respect a lot, Ben Van Roy, and he works a lot on reinforcement learning, and his point of view, he said, okay, in the end, when you build your DRO, all what you are doing in the end is coming up with another loss. Because if you were able to solve this supremum, the inner soup, that is going to result in another loss. It's another loss. It's going to be the expectation, but it's going to be a modified loss. So sometimes that loss is just going to be like a penalty, like the gradient, the square root of delta times the gradient, or whatever. But in the end, you just have another loss. And so why don't you think hard about your loss? I mean, if you think hard about your loss, and basically you capture everything about your risk posture. So, how do you feel about not knowing the environment and everything? And you just think hard about that, then you have your loss, and then you can do away with the error, right? And I think it's a little bit the philosophy of what you were saying, if I understand correctly. I mean, you say, well, I mean, what if the stuff that I don't know, I just model as a confounder, there's an infinite dimensional confounder, and I put another prior on that, so I'm, basically a non-parametric guy, and I go, and sort of like move on. And I think from a decision theoretic standpoint, we know that is not the same, because we know that thing would be a von Neumann-Morgenstern decision theoretic. In the end, you have expected utility. And we know that this min-max, that I said a little bit about that, the Ellsberg experiments and the Gilboa and Smedlier 2008 paper in Econometrica, it tells you if you are going to have the min-max rule, you need to relax this axiom. And so we know it's not the same. But practically speaking, right, I mean, in terms of being pragmatic, I think it's perfectly fine. It's the same. Now, the only thing is, well, it's not the same, but it's kind of like a very reasonable way to move forward. In the end, my response to Ben, for example, and is that, and it's similar, right? I mean, it's like a lot of what is happening, I think, in terms of how we are trying to assimilate what's going on with AI and the advances that are happening before our eyes is interpretabilities. What is it that this machine is doing? Why are we doing what we are doing? And it's not enough that you have an amazing intuition, right? I mean, the rest we also kind of need to buy in. And the DRO framework is a way to at least make it discipline. Say, okay, you have let's assume that we know everything, and then okay, then if we don't have any uncertainty, this is the problem we need to solve. And if we don't know, let's model what we don't know, and then we introduce this layer, and it kind of becomes more orderly, more disciplined. And then the loss function that results is just kind of like a consequence of this. And we can track basically what that means in terms of the worst case distribution, etc. So I think pragmatically, if you have a lot of intuition where you can come up with your own laws by either thinking really, really hard about your laws or by doing this device of, kind of doing some non-parametric base. I think that's perfectly fine. Now, another advantage of the DRO stuff is that the people have been thinking and working about solving games, like min-max games, and that is, you can latch on into that. Also, people have been thinking a lot into, about, sampling, MCMC, so you could also do that. I think, it's not, DRO is not the only, definitely not the only way. But I think from a pragmatic standpoint, I think it's perfectly reasonable to do. All right, so I was saying, this is, when you take this approach that I want to take is discipline, and you want to kind of incorporate, for example, what the market, in this portfolio optimization example, you want to incorporate how the market participants evaluate or perceive future risk. What I said was, you can construct cost functions that depend on the outcome. So this AI depends on XI. XI prime would be the adversary, and depending on the information that we observe, and you can make the transportation cost be low if you think that the market participants collectively think that there is going to be uncertainty on that asset, or the transportation could be high if the market participants think that there is no uncertainty or no volatility in the future for that asset. So that's something that we feel that you could get this red curve using an implied volatility index. When you have general cost functions like this one, you no longer have a closed form solution, so you can't really, it's not a penalty, so the solution is not going to be, this A depends on the outcome of the XI, so it's not as neat as the square root Lasso solution that Pepe showed a few minutes ago. In that case, so this is, the combination of econometrics and optimization, right? So that's optimization, conscious econometrics. So I'm going to tell you about what type of results are known in terms of computation and what type of results, are still to be, found. So in the case when you have linear decision rules, and for these types of cost functions, or even situations where the transportation cost of the cost of perturbing is a convex function of the difference between xi and xi prime, that would be also that will also be fine. It's strongly convex, so it has to have some smoothness similar to this one, or it has to be a norm. So this part is basically perturbation analysis, and I'll discuss why this is useful. This is not only useful for getting intuition and about what is the behavior of the worst case adversary, but it's also useful in the statistics of this problem. So the duality result. So let's reason out what is the optimal scaling when you have something like this, and this matrix A is positive definite. Okay, so let's just think a little bit about what would be the worst case distribution. So it doesn't really, the theta doesn't really play any role. So let's think about how to reason about this. So if you think about this cost function, so when I write expected value of delta is the size of my perturbation, so it's delta AX delta, and that's equal to delta like this. Okay, so what I can do is I can introduce a scaling here. Delta bar is going to be square root of delta, delta, this is is the worst case adversary is going to be a square root of delta times delta bar. So you can see that the cost, whatever was my cost function, so if my cost function is something like this, then this is going to be homogeneous of degree 2, that's why I put the square root of that. But if it was, if it was another power r, or it's like linear, then that will affect the power of delta here, but it's very easy to guess. Okay? So I'm thinking about, okay, I'm trying to guess what is the shadow price, what is the Lagrange multiplier, how everything behaves. Okay? So just kind of get intuition. So remember that lambda, which is the Lagrange multiplier or the shadow price is the derivative is how much the objective function changes with a small change in the budget. Okay? So I'm going to start thinking, okay, what happens when delta is small? How that impacts the behavior of my worst case adversary. So when I do this rescaling of my adversary is going to be a square root of delta times something. Then I plug that in here and I get the constraint becomes delta bar AX delta bar less or equal to 1. Yeah, so this is now properly normalized. So that means the adversary is going to move something that is of order square root of delta. And so that means if I plug in my y here, which is the worst case distribution, if I solve this problem, if I were to solve this problem, it's going to be x plus the square root of delta times this delta bar. Okay, so that means the optimization problem is that if I solve it, like I just need to compute some delta bar which is optimal. It's going to be of order 1, doesn't depend on delta. Complicated, but I don't care. The point is that this expectation is going to be just the expected value of my original loss, x plus this theta times square root of delta and this delta bar, whatever that is. Let's assume that I have computed the optimal one, right? So as long as my L, if my L is Lipschitz, then I know that this is roughly going to be the distribution at the beginning, the expectation at the beginning, plus something that is of order square root of delta. Okay? So that means a small change in the budget, if I go from delta to delta positive, from delta positive to delta equal to 0, the change in the objective function goes from something that is the center of the ball, expectation, plus a square root of delta to something that is just the center of the ball. So the change in the objective function is of size square root of delta, and the change in the budget is of size delta. So the Lagrange multiplier should scale like 1 over square root of delta. So the numerator is square root of delta and the denominator is delta. So that explains this scaling here. And so when you solve, now what you can do is you can plug in that scaling in the objective function. You can look at the dual, everything is going to be properly scaled like this, and you can solve asymptotically what is the best strategy. So that's how you can sort of guess what would be the strategy. So once you introduce that scaling, the scaling is essential so that everything works out nicely. You can solve this. You have something that is precise here, and then you can solve this optimization problem. So the discussion that I have said here of what happens, what is the order of the Lagrange multiplier, like how the shadow price scales when delta is small, and how the worst case distribution scales, just a perturbation of size square root of delta when delta is small. That is general. I really didn't use the fact that the decision rule is the decision of the portfolio optimization. And once again, let's keep in mind that the case where theta is weights of some portfolio, I'm really not using that. I'm just using the fact that L in the end is going to be Lipschitz, and I'm using the fact that the cost function is locally quadratic. If the function is not locally quadratic, then that is going to change my scaling here, but worst case adversary is. So that's something you can do in general, not only for this. Now, when it comes to solving the optimization problem, the actual solution, right, is really useful that this is a linear decision rule, because in that case, what we can do is we can basically sort of like say, okay, when I know that this is just theta transpose of the form theta transpose x, I know exactly what direction I need to move. I need to move parallel with respect to theta. That's the direction that most damage makes for this loss. So if I'm optimizing, so once again I'm optimizing here over general directions, delta, here. If you look at this adversary is going to optimize over general direction delta, and it wants to maximize the damage it does in this loss. Well, it better moves in directions that are parallel to this theta. Right? That's going to affect the loss as much as possible. And so those directions that are parallel, of course, they refer parallel with respect to this geometry. And so that's why you have this correction of A inverse. And so that's why this delta in the end is going to be something that is parallel with respect to the geometry generated by this matrix. And by this, now the bolts are distorted by this A. And so that's the parallel condition. And then you just need to kind of figure out what's the right amount in that direction. So the one-dimensional, the linear decision, the linearity in the weights of the portfolio, or the linear regression, or these problems that are where you need to estimate something that is linear, makes the inner optimization problem tractable, because it becomes just a one-dimensional optimization problem. So this pretty much is what we can do. So there is a large literature on solving these games, and now I'm telling you that's the kind of the state of the art. So there is a literature on solving these types of games. The point is solving the games sometimes can be difficult, and the literature that exists, the papers of Dan Kuhn and the ones that I mentioned earlier and last lecture, but are in the slides, reduce or reformulate these problems using very large dimensional sort of So the point of the result, I mean, what I want to show you how a sort of model result looks like that uses a stochastic gradient descent. So the current state of the art, if you want to go beyond the cases where the center of the ball doesn't have finite remaining points, or you want to have a result that has complexity in terms of computational complexity that is uniform in the number of points. So you don't want to kind of put in your solver, in your convex optimization solver, something that has lots and lots and lots of constraints, as many as number of points. Then you want to resort to a stochastic gradient descent, or you have to, if you want to kind of import the machinery of a stochastic gradient descent, the only way we have at this moment to do it is situations where the loss has to be, the composition of something convex and linear, right? So of course you can always do something more general and throw in a neural network. We have done that as well because we don't not only have the luxury of sort of having this type of structure, but the guarantees that exist in these problems are not as strong as the ones that I'm showing here in terms of convergence for the stochastic gradient descent. So the point of this slide is to give you a sense of what what's the state of the art, what are open problems in terms of complexity analysis and optimization algorithms for these types of games. Yes, so could be something like the cost between x and x prime, the cost of x and y, say, could be a of x minus y, but this has to be locally strongly convex at 0, or like c xy, in this case is x minus y, ax, x minus y, transpose here, and ax is positive definite, uniform. So the type of thing here, so the stochastic, what is hidden here in this stochastic gradient descent, in this result, the stochastic gradient descent, is, there are two things, is the envelope theorem. So when you actually try to write the gradient of this, you can swap this max with the gradient expectation, you compute it, you ignore everything, and then you evaluate the gradient at the optimal value, and this theorem cares about the computational complexity of computing that optimal value. So that's this log of 1 over epsilon is doing a line search, this one-dimensional line search. Now, one-dimensional optimization problems are still being hard. So for that, to deal with that issue, we need to kind of say, okay, I can tell you a priori in each iteration what's the interval over which you need to find this solution, this maximizer, and that integral is not going to start growing and growing and growing as you go on your stochastic gradient descent. So that's what I mean by kind of like a result that would say, suppose that you have L of theta 1 y, comma theta 2 y, theta 3 y. That's not. Okay, so it's like only one theta. Yes, when this theta becomes a matrix, that I don't know. No, that analog to that problem doesn't exist. So those were the inclined to do optimization. Okay. So now I talk a little bit about the dynamic view of optimal transport and these kinds of problems. So it turns out that we also, once you actually do this kind of analysis, you learn a lot about the structure of the worst case distribution. So it's in this case, even though the cost function depends on is not a it's not a norm and depends on x. You see the delta is something as a function of delta parametrically in this delta. The worst case distribution fixing a decision depends on is linear. So that means we know we know how the worst case distribution looks like and how dynamically it moves, like these points. You know, if it's a classification problem, so this is a, you know, this is a hinge loss classification problem. What we know this is going to do is, you know, we know that it's going to be a start moving. The worst, the least favorable distribution is such that, you know, the adversary starts to kind of flip the decision. So this was a point that was a yes, and then becomes a no, or a label. You know, it starts assigning the budget closer to the boundaries and in directions where the principal eigenvectors and eigenvalues of this AX sort of you know are sorted. So you can see that this is A inverse. So it's the same. Is this intuition in this choice where you know there is some sort of notion of volatility. In this case, is with respect to the standard coordinate basis. So you know, first direction, second direction, etc. Right? I mean, in the orthogonal basis, and here, well, it depends on it's a positive definite matrix, so it's now going to depend on the principal components of this matrix A that depend on the outcome X. So this gives you a lot of flexibility to kind of you know, model this. That you know, preferred directions of the worst case adversary. So I said, so this is the paper I mentioned that discusses all of these reformulations. So when the case is the maximum of affine functions or linear functions, you can pose this whole thing becomes a very big optimization problem that is convex. And so the drawback of that case is that you need to add order n dual variables, where n is the number of points. Whereas this case here, this complexity resolve is uniform in the number of points. Yeah, so it's just it doesn't matter. Your initial distribution could have infinitely many points, and just the nature of a stochastic gradient descent. Okay, so let me. Okay, so are there questions? I'm going to move on to something. No? Okay. Yeah, it has to be linear at this moment, right? And multilinear cannot be done yet. So multilinear, multi-level logistic regression, for example, is something we still can. There is no analog for this thing. Now, I think what comes next here is is basically kind of looking at the extension of the M estimation for these types of problems. But I think I don't want to rush later, and instead I want to show some animations before we move to that, because I think at least I don't want to show you the animations when people are sleeping. Yeah. Yes. All right. So, okay. So these are cool images. Let's see how. Your keyboard cannot be identified. Okay. Something tells me I shouldn't skip this. Okay. So this is one of the I thought for people who haven't seen like optimal transport, you would see this is Pepper mentioned about in his talk is also a fine. It comes from the fact that the distance between two Gaussians is just one transformation of one to the other. And this shows this dynamic view of optimal transport where the center was a Gaussian and you cannot move it. This is one of the nice properties about you having this principled approach of kind of modeling what you don't know, that you can do. You can do sensitivity analysis as you increase the budget, and you can get a sense of how the least favorable distribution starts looking in a way that is informed by the objective function of the problem. And then before somebody asked about what a minimax theory looks like, or what is required, right? How that problem is posed. So in the case, just as a particular example, like in the case of mean estimation, the statistician would like to compute. So remember, in this way of thinking about robust statistics and DRO, the statistician thinks that the data that was given to him or to them, right, contains the truth. Right? So it has been corrupted, this p hat, and somehow he needs to find a way to uncorrupt the data and estimate, does the data, does the decision of the statistician based on the data. This is the empirical mean of the data corrupted, and his target is the true mean, okay, or whatever is the parameter. But in this particular case, the mean. And now the expectation here is the expectation of the corrupted data, because that is the law of this p hat n. It came from that corrupted data, right? And so what is a natural rule to do, but we do not know is minimax optimal or not. It would be, well, clean the data. So you have given me some data that is corrupted. Somebody has corrupted that data according to some attack. I clean the data first, and then I find some, just a plug-in estimate, right, after cleaning. The classical corruption mechanism is optimal transport in that literature. That is a very, very drastic sort of attack, which is total variation. So total variation is a particular case of optimal transport when the cost function is just the 0-1 loss. And what is minimax? Well, because it's a lower bound, the way in which you define minimax, you can get away with just the probability that the loss under the distribution that generates the data, the contaminated distribution, is larger than this, the largest possible bound. But you can just put the expectation. It is basically the rate at which you converge to zero for this quantity here. And so what happens is, this is the way the statisticians play this game, which I think is very pessimistic. I don't think this is the right way of measuring it, but I'm going to tell you how they do it. They say, so I'm a statistician, I'm going to find a way to decontaminate the data, or whatever, figure out how to do it. This is one way of doing it, but might not be minimax optimal, right? The mean. So figure out one way of doing it, whatever it is, and then the max part, the standard case is just maximum over all possible ways of generating the data. So this is the distribution, and this is the part that I think is super pessimistic, is that also the adversary can also affect the distribution this way, right? Before you make the decision. So that's the thing that is kind of inconsistent, I think, but that's the way they do it. And under this particular way of defining what minimax is, so basically, is there a question? Yes.
So I think I'm confusing myself on the order of play and the way in which the infs and soups show up in order. So I just want to clarify that this inf that's all the way to the left, the one that's choosing this data, has no knowledge of the way in which the contamination has occurred. And here the contamination is So I'm going to try and be agnostic to what type of contamination took place.
Right.
Is that the right way to interpret the order?
This is you are exactly right, and there is a mismatch between the way I told you yesterday, in which I told you the adversary has made its move in terms of the contamination, right? And it was like, yeah, that makes kind of sense, and you know that is a very beautiful picture. And the way in which the statisticians today measure whether an estimator is good, and the way they measure it is they take a very pessimistic approach in which it's different. The adversary actually moves after I make my decision. So under this way of thinking about the world, it's going to be a lot easier to find things that are really max optimal. Because like you are playing an impossible game, like just you're never going to go to zero as long as this perturbation is large. He always can, after you're done, change the distribution. So, that's why I don't like about this, but this is what they do it, and then it's minimax optimal, right? But what I believe is this is actually minimax optimal in a much more realistic sense, where you get to, the adversary moves first, and then I get to know something about how the adversary does move. But that theory still does not exist. But this addresses your question, okay? So I don't, instead I want to tell you, okay, so now here's one, one important difference between DRO and the sort of perturbation analysis that I was showing like a few minutes ago. I told you the adversary moves the square root of delta, right, for example. And then I just argued that the shadow price is, the objective function, if the loss is Lipschitz, changes by the square root of delta, divided by delta is 1 over the square root of delta, and yeah. So the intuition is that in DRO, the least favorable distribution has the following characteristic. Everything changes a little bit. Everything changes a tiny bit by an amount that is small, controlled by the diagonal of the cost function and the budget. Yeah? If it's locally strongly convex in the diagonal, so when the cost is 0, when x is equal to y, then square root of delta. But this is not what if you want to use still optimal transport to obtain estimators that are minimax optimal in that statistical sense, and are modeling exactly what the statisticians want, which is this total variation, then you cannot be using the same type of cost functions, and then the nature of the worst case adversary changes completely. And it has to be like that, right? Because, well, in this case it's not worst case adversary. In this case is the helper, right? Because we have, now the point of this result is that tell you that the mean correct first and then estimate later works. Okay. Now the best rectifier, so the optimal distribution that rectifies, that's not is something that has to be consistent with the intuition of removing outliers. And to do that, the theory of optimal transport, the flavor of the theory of optimal transport that we use involves cost functions that are not convex but are concave. And in the rectifier, the optimal rectifier, as I was talking about as the optimal worst case adversary that changes a little bit, square root of delta, every point changes the square root of delta. In this type of, in this theory of robust statistics, the optimal rectifier, the way it does is only changes a few points and it moves them a lot. Okay. So the case where r is equal to 0 again is total variation, but we change it in this to obtain something very robust and that is tractable via stochastic gradient descent. We just put some relaxation of the total variation case, r will be 0 and 1, so that we can apply the machinery of a stochastic gradient descent for these estimators. So here is one example. So this is a simulation where I gave this data was corrupted, is here, and I apply this optimal transport view of producing estimators that are statistically robust. This is not distributionally robust. And what I'm showing here is what is the distribution, the rectification distribution, the optimal rectification distribution is doing. So using this concave, this is I is equal to 0.5, so I have moved the data. The mathematical program, the optimization program just finds the best distribution, finds what are the optimal ways of actually rectifying the distribution. That's the beauty, right? So in this picture, obviously, it's, the outliers are these orange things, and then it moves it. But the point is that this is just done with a stochastic gradient descent. In d dimensions, you do not know what is you cannot be plotting, right? It just becomes very hard. So, but you can see that this is what happens when you use this concave cost. This is what the statisticians sort of like see as an optimal, as robust. And if you use optimal transport with the cost functions we use in DRO, which are convex costs, and if you do mean or you do max, this thing doesn't work. Yeah. So the statistician, this is not robust for the statistician. Okay. So that's the same thing happens with these linear decision rules, like for linear regression. And once again, if you have, it's the same optimization problem that I showed you before. I have to be patient here. Animation. Is for some reason it's kind of slow, but this is a linear regression problem again. You don't see where the outliers are, but the mathematical programming problem will just automatically kind of find where the outliers are, and it's going to just remove them. So that's it. Those are the animations I wanted to show with regard to that part. I think something that is kind of a little ugly for this, and this is another optimization challenge. Well, I hinted to, yes.
If you don't mind, could you go back to the example, the 1D case where you were correcting the outliers?
Yes.
In the statistical robust version of it?
Yes. This example or this one?
I have a question about both.
Okay. Yeah.
So starting with this one, the way to rectify the outlier data to be statistically robust is to kind of push it all the way.
Yes.
And I guess here it's like pushing it to 0.
Yes.
But then to be distributionally robust, maybe this is the point, but I don't think I saw a difference in the outlier data and the rectified outlier data.
Yes, that's the point.
I don't think I followed them.
Because in the distributionally robust, in this case, this convex cost is going to make it in such a way that everybody moves a little bit. So you see these things kind of moving a little bit. They try to be either close or they separate, but everybody moves a little bit. Now if you say, well, but that's Jose, that's just whatever, just put a concave cost. Why did you choose convex cost? Then, because the agent chooses later, right? So it's first I make the decision, then the agent chooses later. And if I put a concave cos there, then the objective function is going to be infinity. So that you know, I cannot formulate it like that. So I'm stuck with convex cos, and then you know they don't actually fix the data. They don't fix the contamination that is what the statistician sort of is thinking when it's you know, outliers or corruption.
So I see that in phrased in this way, the statistical robustness is not what distributional robustness is trying to tackle.
Right.
But I don't think I see the problem that distributionally robust is trying to tackle here if the outlier data and the rectified outlier data are the same.
Because that was not the point of this. The way to see that part is with the real life example I show you.
Okay.
Yeah, is where you know you can see that I give you economic theory that tells you this is a concave sort of Pareto frontier, and then when I do outsample, it's just completely opposite, right? That thing is illustrating that. Yeah. Yeah. I wanted to say, so in addition to this, just one thing that is, yeah. So the good, the bad, and the ugly. So the problem, the only problem, well, it's a major problem, but it's an also optimization problem. So these rules are going to be minimax optimal. I mean, we do it only for linear regression. We do it for a mean so far, but I believe on substantial generality, and that's still we are kind of working on that. But this is going to be a way to do, you know, kind of like a general framework to produce decision estimators that are minimax optimal in this very pessimistic way, right? There has to be another paper written about what's the correct, less pessimistic, something more interesting. But now this econometrics, optimization conscious econometrics, how hard it is to compute those decision rules that are optimal in that setting. Turns out it's pretty hard. And the reason is, so in principle, DRO problems are easier to play. It's a game, right? It's a min-max game. But it's an easier game to play because you as a player, you are the statistician, you are the mean guy, the minimization part. And what you typically are doing is you are maximizing something that is convex. So the maximum of convex functions is convex. And in these problems, you are going to, you know, face a convex optimization problem. That's the way you have to play. Okay? You play something that is a solution of a convex optimization problem. But it's a harder game to win because you are playing against an adversary who chooses after you choose. So it's harder to beat this guy. But playing the game is easier because the correct way of playing the game is solving a convex optimization problem. For the statistician, he faces an easier game to win because he goes after the adversary. But to play that game is harder because he needs to solve a mean problem, and now the outer mean, which is you, the statistician, is solving an optimization problem which is the minimum of convex functions. And that is ugly, right? So the minimum of convex functions just has lots of kings, and this is exactly key. So this is a challenge in optimization, kind of removing these kings. This is really bad, kind of going on all these things. And that's a research agenda we are pursuing with the group in terms of how to remove this. And the key is to now, okay, you need to kind of play this game between being an optimizer and being a statistician, because you want to say, how do I inject noise here in such a way that I don't destroy the minimax statistical optimality. So I have room to smooth these kinks, but I just have to smooth them in such a way that my estimate is still minimax optimal, right? And then I look at, as I send the sample size to infinity, how that actually, you know, affects the computational complexity of the problem. This, for example, this is a characterization of But basically, I think I have a better picture. So when the loss function is convex and Lipschitz, and you have something that has a positive density, and you have some regularity conditions that are mild. Basically, this is telling you the picture that you saw, where you have these things that are out in the tail, and you start moving them. This result is telling you just that picture. It says that the difference between the robust estimator, the inner mean, and not doing anything, so the center of the ball, just says remove the things that are out in the tail and just put them at zero. So assuming that this L of 0 is equal to 0, so all of these guys, that's the green part, and just centers it at 0. And then there is a Lagrange multiplier that solves some equation. So this gives you the structure of the worst case or the best case rectified. Right? This again is the same duality result that we use in VRO can be applied here, because fortunately the function is linear, so mean is the same as the maximum of the minus. So it's the same duality result. In fact, here that is applying here, instead of a positive lambda, you have a minus here, and instead of a penalty of a cost that is negative here, you have a plus. So this duality result is exactly the same duality result, and the operation sort of the optimization principles that operate in this type of optimization programs are very different. In this case, it's basically linear programming here, so you know that the optimal solution is achieved in extreme points, and then you just kind of compare which one is either the right or the left, and so it's basically linear programming or maximization of convex functions, and that is achieved in extreme points. So I'm very excited about this area. It's very, very new, and it's it has, I think it provides a very rich interplay between optimization and statistics. Once again, we know what's the minimax optimal estimator. I mean, we know how to produce it. It's anti-hard. But we know what the hardness comes from. The hardness comes from the kinks. And we know that if we smooth the kinks, then the problem becomes more tractable from an optimization standpoint. So let's use statistics to smooth the kinks, right? So to say, okay, how much I can inject of a smoothing in the algorithm in such a way that my estimator is still minimax optimal, or maybe I pay a logarithm price or so on. So the philosophy, I think, is pretty, well aligned with the topic of this sort of discussion of optimization conscious econometrics. Now I'm going to go back to this other. So I think I pretty much, I have said what I wanted to say, and in terms of conceptual understanding, it's pretty hard to absorb, tools and techniques in just 4 days. I think I've been trying to kind of give a much more sort of conceptual idea of what are the open problems, what are the interesting cases, what are differences, and you can look at the papers and which are the ones that I said at the beginning of the presentation, and so now I'm going to use just a few minutes later. I'm going to go back to the arrow. So the arrow, right? And I'm going to talk about the statistical analysis of the DRO estimators. And for that, I'm going to start with the case of the N estimators, right, that you probably are very familiar with. So in the context of empirical risk minimization, so which you want to solve the empirical version of the problem, and you want to solve our problem, you need to take the gradient and make the gradient equal to 0, and that is the M estimation problem. The way this function, which is your loss, expected loss. You have Pn is your empirical sample, and as n goes to infinity, you have the law of large numbers, and you want to impose assumptions, for example, Lipschitz conditions, standard assumptions that are in this book of, well, there are many books, but the one that is known in optimization is this book of Shapiro, Blanchet, and Ruchinsky. And, you know, under the assumption that exists of this Gaussian process, and you have this approximation, say, the weak topology on compact sets, then you are indeed, this is what that means. Then you can show that you can estimate, you have a central limit theorem for the optimal value function. So that thing is, that I'm taking as a review. I'm just telling you what is a standard. And you know, it's under those assumptions that are satisfied typically my conditions, you get that the central limit theorem for the standards of empirical risk minimization estimator just converges to Gaussian. So what are those standard assumptions? So in addition to this, well, that book actually refers to this one, Van der Waal. This is not there, and Wellner. So this is the type of condition that ensures the existence of this central limit theorem at a functional level in which converges topology and compact sets. Is that the loss function is locally Lipschitz, and the Lipschitz constant has finite second moment. So that was an example of something that.
Just one question, because I think you have something that it's like more general than what we usually see on the
Really?
metrics courses. Because you actually have if you go below, so you have this max of, is it the max of the Gaussian processes? With G of theta is Gauss-like process and it's by theta.
Yeah. So
because the typical results that we have, we're seeing there's identification, right? So there's a unique minimizer.
this is not needed.
Yeah, so that's all it says. That I think
Yeah.
you have a linear result.
Oh, interesting.
The minimum,
Yes.
the minimum.
Over the set, the arc mean, which might be not unique. Yeah, that's correct. Yeah, I didn't realize, but okay. So you can. There you go. Nice thing. But is because I'm not identifying the solution, I just want to kind of find the performance. It's a central limit theorem about the performance. So now, when you want to identify the solution, you do need something stronger, and it's the same type of result, but now for the gradients of the functions. Now, the same local Lipschitz condition you have to assume, but now for the gradient of the functions, and it's the same principle. So this is like at least in optimization literature, these are results by Alex Shapiro from 1980s, and you know that in those cases when you have these type of things, the standard machine in optimization is to say you need to have some sort of expansion, right? And Alex Shapiro has a book with Bonans on. This is a very famous book on kind of perturbation analysis. So they say, okay, how do you, if you look at optimization problems of this form, where you have indexed by this vector V, and you look at the solution to these optimization problems parametrically in V, you know, when can you find expansions, right? Taylor expansion, and this is about the delta value for this kind of thing. So. So the sort of assumption that you know this results on regularity. So the thing is, what is important is that you see this type of result has nothing to do with the statistics. There is no n here. This is just something about the population distribution of the problem. It's just optimization, the theory of optimization and perturbation analysis of the optimization problems. And so that's something that you go and you look at the book of this is of Shapiro and Bonans, and once you have that type of result, so this is called second order regular. It's a little more general than saying that the Lagrange multipliers are smooth So
It's serious in the Blanchet period. You usually install. You have an if and a soup. The soup is over Lagrange multipliers. So you have multiplicity of them.
yes, yes. So that's correct. There is something. There is when you write the constraint region, which is important also in the results. You need to have constraint qualification conditions. So linear independence of the gradient at the boundary. You cannot have linear independence of. You have unique in a neighborhood of B of beta when you do your perturbation. But the point is, so what I'm trying to do is like I'm assuming. Suppose that you have in place those assumptions, right? Non-DRO. This is non-DRO. This is just I'm saying, okay, you pick your favorite type of assumptions for the case of delta equal to 0. That's all what I'm saying. You know, whatever you have. In the book of Shapiro, he provides sufficient conditions to have an expansion of for the optimizer of this thing here. So for this optimization problem, now if I look at this V in terms of directional differentiability, so Hadamard differentiability, so I go borrow the results of Shapiro. This is not DRO. This is not even statistics. This is just optimization. And then I have directional derivative with respect to any direction V. I have an expansion that is of this form. Then that in combination to the empirical process result, this type of thing. Okay, now that's statistics that you can look at your van der Waals-Werner result. The combination of these two is telling you that you have a central limit theorem for the optimizer, and in that case, it is assumed implicitly in that theory that this is not partial identification. This is a unique optimizer. So for the value function, you don't need that. It's going to be just the infimum over all solutions. But for the optimizer, well, you need to have an optimizer for the optimizer. Right? So this has to be unique. And so the strategy here is, how do you translate this to DRO? Well, the way to do it is you need to have an asymptotic. First, step number one, you do an asymptotic expansion, right, of the objective function. So you fix theta and you do the inner maximization problem. You do exactly as I said before. You rescale. So there was delta here, but I introduced delta bar. I introduced proper rescaling. Typically, that's everything about the diagonal, as the case x equal to y. It's all about that. And then this is just the primal problem, right? You massage the problem a little bit. And here you have another DRO problem, but everything is nicely properly scaled. So you can send delta to 0 formally and get the solution. And you can use the duality to this would give you you have an upper bound here because the maximum is going to be less or equal to the solution you obtain when you guess, right? And you obtain a lower bound because the dual, it has a mean here. So in the dual, you plug in the optimal lambda that you obtain when you plug in the scaling I mentioned before with the lambda. And then because that's a particular lambda, that gives you an upper bound. Because it's an infimum over lambda, you plug in the lambda, that's greater than the infimum over all lambda. So that the duality allows you to give upper and lower bounds that typically you can guess. You see, you can send delta to 0, and this is going to be the gradient of L. And you have here the norm of delta, so you can solve this optimization problem. So once you have that kind of insight, you can just start plugging in what is the kind of optimal value of delta, so that you know that this thing is of order 1 over root n. Well, to have something that is not, it has properly scaling, so that the optimal choice of So so I'm gonna show. I'm gonna just simply say it here. Yeah.
Because like based on the things that you showed us before, for example, I thought that you were going to give me a Blanchet here type of result for the min-max zero problem for an arbitrary t. You know, like you said that the results that you had at the beginning of the estimated were really based just on the unity and sensitivity analysis of
Yes.
the optimization problem.
Yes.
So I thought you were going to take these two like, well, when you do the soup, that's just another loss.
Yes.
Depends on whatever baseline distribution you're using.
Yes.
So I could always try to see, like, if I were interested in the value, that's the differential with respect to the underlying p.
Yes.
But it seems like you're proceeding differently, right? You are doing what you know about that optimization problem and how that relates to p of n, and then you're going to try to connect to.
Yeah. So I do so step. So I write this as minimize dp p0 less than delta expected value L y theta, yes? And I write this as expected value under P0 of L x theta plus the square root of delta times expected value under P0 1 half norm L x theta, right? And then plus little o of delta, okay? And then, so this is general, this is true for any P0. There is no statistics here. This is the bonanza, this is perturbation analysis of this optimization problem. This is a max here, by the way, sorry. And then, what I do is I say, okay, now I'm going to use my hat of a statistician. I'm going to put an n here. Yes? And now I know that there is an expansion for this that has 1 over root n. There is a law of numbers here that operates. And so then, when delta goes to 0, I need to match this delta, this whatever happens here, I need to match with the 1 over root n.
You don't need to make that error curve that was all delta to not make it OP.
Yes, yes, so okay, so that's okay. And so that is the character that I am having under the rock. So there is indeed a Pn here, and the reason is hard is when everything takes values in a compact set, that everything means the excess. Okay, if the P infinity distribution takes values in a compact set, then there is no problem. This thing is uniform. Okay, but when this Pn doesn't take values in a compact set, you see what is going to happen is that in the sample, this is correct, but I could have a sample that has infinite variance, for example, and this thing is going to start growing and growing and growing. So everything that I said here, thank you, relies on, this is the standard approach when when the data just takes values. The population distribution takes values in a compact set.
In most cases, for the case that you show us how to solve explicitly, say the linear regression problem with the Blanchet transform. So the leading terms that you get, so what is it the lasso or because I don't see this little lasso anymore?
This, in that case, this leading term, well, because I have chosen here the L to distance, not the L infinity distance.
Okay.
Yes, so if I had chosen, then you would see something slightly different in this problem. But you can see that the loss here, the gradient of the loss as a function of x, yeah, it has the parameter beta. Yeah, but yeah. So okay, so I want to finish with so then once you have this, basically you can just plug in the P infinity here because just plugging estimate with the population loss is is going to have another 1 over root n. estimation type analysis, and you know, for example, you have this correction, right, which is the natural correction once you add this, and this square root of delta becomes another something one divided by root n, then you see that's exactly what pops up in the central limit theorem here. And so this is this correction. And for the case of optimizers, when you adopt the view of Shapiro, you already have the direction differentiability of the optimal solution. Then again, you're just adding the gradient of the correction. This V is just precisely this function. So you can just plug in the population distribution here. So it's easy, at least in the compact case, to obtain asymptotic statistics of these DRO problems. Because DRO with optimal transport includes phi divergence and K divergence, I told you before, then, you know, the very, very similar translation occurs. And that actually is one of the papers I'm citing I wrote with Alex for this. And we do it only on the compact case, and we cite some references of cases where we do like the realization of the compact case, and it requires, that requires kind of assumptions on moments so that you can control how the largest value sort of like grows as the sample size increases. I'm gonna close with this thing that I think is really cool. Okay, so once you have you have a central limit theorem for the optimal solution. Suppose that you have identifiability, not partial identifiability. You have the theta stuff, okay? Now, there are many confidence regions that you can get, right? So we never that's kind of interesting, right? So which confidence region? Of course, I mean, you want to do like a confidence region that maybe has the smallest volume, right? But there is a very natural confidence region that is suggested by the primal problem. So the confidence region is the following. So look at the uncertainty region. This is the distance between Pn less or equal to delta. Yeah. Look at all the P's that satisfy this. Yeah. This is U delta Pn. Now pretend that you solve the optimization problem, so you optimize, you find the best portfolio or the best linear regression parameter for each of the models here, okay? And then collect all of these solutions, right, in this world. And now you can think of this as a confidence region if the beta is chosen in such a way that it contains the true solution with 95% confidence. Okay? Now this confidence region will be informed by the primal problem, by the DRO solution. So it's not any confidence region. And what turns out happening is that this confidence region, so if you kind of go with a confidence region that is, for example, the minimum sort of volume confidence region, that confidence region might not contain the DRO solution. So it's a little bit kind of not satisfactory that your estimator is the DRO estimator, but your confidence region doesn't contain the estimator. And if you add that estimator, right, and then you make the confidence region convex, that's kind of natural looking, then you have destroyed the optimality. It's not 95% longer, it's larger. So now the nice thing is about this confidence region, the one that you form by doing this, actually contains the DRO estimator. It also contains the empirical risk minimization estimator, and it is informed by how do you think the adversary is going to attack you, and that changes the geometry. So I am showing here examples where I use the LP norm for different values of P, P1, 1.5, P infinity, and then you get different confidence regions. So this is for the linear regression parameter example I showed you earlier. I think I want to just spend 5 minutes just kind of hinting at what is behind this, because it's a beautiful theory and it connects with empirical likelihood and hypothesis testing. And you talk about hypothesis testing in the morning, and so it's a way to kind of do hypothesis testing using this optimal transport machinery, and it's very closely related to VR. So if you look at how do you compute this profile, these regions, how do you actually make, because this looks kind of like an inside. Obviously we don't compute all of these data that satisfy that, but that would be an insane thing to do. What we do is we say, okay, let's look at the problem of minimizing delta such that the probability that the theta star is inside this confidence region, that's at least 0.95. Yeah, it's a 95% confidence region. So I want to find the smallest radius that guarantees that the true parameter is in here. And if you think about, if you just translate in English, right, and just what this constraint says, it says that there exists one model that makes this true thing optimal in the book. Okay? So this event happens, theta star is optimal, theta star is in that confidence region, if and only if there exists one model which is within distance delta of the Pn, one probability measure that is within distance delta of Pn that makes this theta star optimal. So earlier you mentioned, you need to enforce the true model to be inside the ball. But this one is a much more relaxed criterion, because this is saying maybe I have the incorrect model, but I have the correct decision, right? So as long as my theta star is inside of what is achievable, that's fine. And if I make delta sufficiently large, the true model is going to be here, the population distribution. But I don't need that. Maybe I have another one that is similar as far as the decision is concerned. So if you translate in English, what do we say is, okay, let's look at all the models. Imagine all the models here. These are the set of P's such that theta star is in the arc mean of the expected value of P L X theta. Yeah, all the models P that satisfy this. When the L is convex, this is the same as expected value under P, gradient of L X theta under theta, and evaluate that theta equal to theta star, that's equal to 0. It becomes a linear set of constraints. And what I'm saying is that this happens if and only if there exists one model here that makes this optimal. That's the same that the distance between the empirical data and all the sets, all the models P that are in this manifold M, which is linear, is less or equal to C to delta. So this thing, there exists, minimum is there exists one, that's less or equal to delta. This manifold depends on theta star. This is the same as the event theta star is in this U delta Pn. So the way to think about these confidence regions, we compute the projection, we call this R and theta star. This is the projection, is looking at the projection to this space of decisions, which is represented by this kind of linear space, this M theta star. Now this thing is another optimization problem. It's another linear programming problem, because this is the Basel time distance. So this is a linear, this is defined as a linear programming problem. So this object is another linear programming problem. And when we compute this, saying R n theta star less or equal to delta, that's the same as theta star in this U delta Pn. The confidence region, so get the confidence region, we look at the points theta, such that r and theta less or equal to delta. So it's the inverse image of the interval from 0 to delta, where delta is the optimal, delta star is optimal delta. So delta star n is the 95% quantile of r n theta star, which we obtain asymptotically. So this r n star theta star is a scale. Using once again the same intuition, you think a little bit about how this thing has to scale. Well, this is a projection that the scales should scale like, if this is a distance, this should scale like 1 over n. If this is a distance squared, this should scale like 1 over n. And we solve the linear programming problem to compute this optimal quantum. But the point is that this projection function, when you replace this distance by the KL divergence, you obtain empirical likelihood. So this is an extension of empirical likelihood. So if you look at, for example, hypothesis testing using empirical likelihood, you can ask, okay, when is this better than empirical likelihood? From the standpoint of power, local power, and we have a classification for that. It turns out that there is a key quantity that basically, if it's positive, then this is better than empirical likelihood, and if it's negative, empirical likelihood is better. Empirical likelihood is better when your alternative, so the null hypothesis you are testing is the expected value of some computation being equal to 0 against an alternative that is the expected value is some vector divided by the square root of n. And it depends on whether you are perturbing the x space or you're perturbing the, you are adding the perturbation outside or inside the x. So it has to do with if this function varies a lot, if the Hessian changes a lot, then this type of test is more powerful than empirical likelihood. And if this thing has moments that are very high, then empirical likelihood is more powerful. So, I mean, it's a very, very rich, from an econometrics standpoint, I'm not an econometrician, but I know that in econometrics, empirical likelihood is used a lot. And what I'm saying is, there is a very rich connection between empirical likelihood and projections with Wasserstein. There is a connection between projections of Wasserstein and optimal choices of the VRO parameters. There is connections with the hypothesis testing, because now you realize, this is just an extension of empirical likelihood, and you can use everything that you have used. Uses of empirical likelihood can be done here. You can ask, when is this better? This is just the beginning of theory we are doing, and I come here to invite people to work on this as well. So I'm going to finish with that.
And theta star is the output solution that give you theta star solution.
Yeah, theta star, for example, is your linear regression parameter, the true linear regression parameter, for example.
Is it built in the heuristic, or do you need something about the problem for n to be nice enough to project out?
Yeah. So you can define it abstractly like this, but it becomes difficult. So when the loss is convex, then it becomes nice because now it becomes a linear projection loss. So these constraints are linear indeed. And the thing is, it's really, really nice. I think it's underexploited because I tell you something, right? If these are moment constraints, right? Suppose that there is nothing special about the gradient. Okay, this is just the connection to distribution and robust optimization. But now you can abstract, say, okay, whatever. I'm just do hypothesis testing. I want to test the moments are equal to 0. And let's say that I'm talking about like random variables that take value in the interval 0, 1, so that I just free ourselves of technicalities of moments or whatever. So I can keep adding first moment, second moment, third moment. The moments characterize the distribution. have finitely many constraints and some infinitely many constraints. Basically, we look at when this converges over 1 over root n, and this is a way to relax the Basel time distance. And yeah, I mean, I think I really like this. We also kind of, for example, we use this hypothesis test because this becomes an hypothesis test. Your null hypothesis is Pn is inside this manifold against the alternative. And when we have applied it to, for example, algorithmic fairness, where the manifold dictates what fair means. And the cool thing about this is that if you reject the hypothesis, so for large values of this statistic, then this thing tells you what's the cheapest way to make it fair. Right? It's not only telling you, okay, the decision rule, but it's telling you what's the closest point in the manifold. And that will tell you, okay, you know, what's the best, the cheapest way to make the algorithm fair according to that criteria.
Yeah, because fair is predetermined data, and you don't have false flag.
Yes, exactly, right? Okay, so it's unfair, so then what do you do? So that paper we submitted to a conference is called FAC, and that paper has been received by the people who do fairness, like, they have treated it like as a piñata, because like, it's really kind of like, it seems to be the favorite paper they criticize. Huh? But the criticism is something that we didn't intend to kind of address, which is which criterion, how do we define the M? Okay? So we say, look, you know, you define the M like this, like this, like this, there are modifications of this criterion and so on, then you can do this, etc. And they were like criticizing how do I define the M, but I really don't care. I just wanted to say this becomes an hypothesis testing problem, and you know, and if you fail, actually I can tell you a little bit how to make it better, etc. Right, and you know, okay, so we have moved away from this fairness thing, but now we are evaluating large language models like with this criterion, like if this model is you know, safe or is not safe. It's not fair, now it's safe. Okay, so then maybe the paper is still going to be treated as a piñata later, but I think this is really underexploited, I feel. Anyway, I have nothing else to say. Yeah.
Well, thank you so much.